Have you ever found yourself just staring at a massive spreadsheet, this, sea of numbers, and you just know there are hidden patterns in there? If only you could figure out how to find them. Well, that feeling, finding that signal in all the noise, that's exactly what we're going to dive into today with a really cool technique called k-means clustering. So, yeah, how do you find those secrets? I mean, let's say you have the shopping data for thousands of online customers. At first glance, it just looks like total chaos, right? But what if there are these distinct groups, these little secret clusters of customers, hiding in plain sight, just waiting for you to find them? And this gets us to a really common challenge in data science. A lot of the time, we have these mountains of what's called unlabeled data. We know who bought what, sure, but we don't have any neat little groups or categories already defined for us. It's just raw info, and it's our job to find the structure that's already in there. And this is what that chaos can look like. What we're looking at here are 300 data points. And right now, they're just a meaningless cloud. There's no obvious pattern, no clear groups. It's just a mess. And our mission is to bring some order to it. To solve a mystery like this, you need a detective. And in our world, the world of data, our detective is this powerful and, believe it or not, pretty intuitive algorithm called k-means clustering. So what is it? Well, to put it simply, k-means is an algorithm that's built to take all that chaotic, unlabeled data and sort it into a specific number of groups, or clusters. And that number is represented by the letter k. Basically, we tell it how many groups to look for, and it gets to work. Okay, so the real genius of k-means is how it works. It's this simple repeating process. First, it just randomly drops k-centers into the data. Then it goes to every single data point and asks, hey, which center are you closest to? And assigns it to that center's team. After everyone's been assigned, it recalculates the middle of each team and moves the center there. And then it just does it again. And again, assign, move, until the groups are stable and those centers stop shifting around. So that's the theory. Now for the fun part. Let's actually apply this to that messy cloud of data we started with and watch the magic happen. All right, here are our 300 points again. This time, though, we're going to make a bit of a hypothesis. We're going to set our k value to 3. We're essentially telling the algorithm, hey, I've got a hunch there are 3 distinct groups hiding in here. Go find them. And boom, just like that. The algorithm's first move is to place 3 initial centers, they're called centroids, randomly on the plot. These red dots are just the starting guesses, the first anchors that the algorithm's going to use to start organizing all that chaos. Now, after the algorithm does its thing, assigning points, updating the centers over and over again, this is what we get. And honestly, it's pretty amazing. That random cloud has been sorted perfectly into 3 distinct color-coded groups. Our red dots, the centroids, have found their true homes right in the heart of each cluster. Chaos has become order. But hang on a second. This brings up a new problem, a little wrinkle in our story. We got this beautiful result, yeah, but it was all based on an assumption that we made. I mean, how did we know to pick 3? It worked out great, but was that just a lucky guess? What would have happened if we'd said, hey, look for 2 clusters? Or what if we told it to look for 10? If we choose the wrong k, we could get a totally misleading result. So this is a huge deal. We need a better way than just guessing. And luckily for us, data scientists have a really clever technique for this exact problem. It's called the elbow method, and it lets us find the best number of clusters in a systematic, data-driven way. It basically takes the guesswork right out of the equation. So the elbow method uses this metric called the within cluster sum of squares, or WCS for short. I know, it sounds super complicated, but the idea is actually pretty simple. It just measures how spread out the points are within a cluster. Think of it like a compactness score. A lower WCS score means the points are all huddled together nice and tight, which is exactly what we're looking for. So here's how we use it. We run the k-means algorithm over and over again. First, we tell it to find just 1 cluster, then 2, then 3, and so on all the way up to 10. And for each run, we calculate that WCSS score. When we plot those scores, we see this really clear trend. As you add more clusters, the score goes down. And that makes sense, right? If you have more groups, they're naturally going to be smaller and tighter. But we can't just keep adding clusters forever because that wouldn't tell us anything. We're looking for the point of diminishing returns. We're looking for what's called the elbow point. It's that spot on the graph where the score stops dropping so fast and starts to level off, forming a shape that looks kind of like an elbow. And for our data, that elbow is crystal clear. Look at that. the score plummets, going from 1 to 2 clusters and again from 2 to 3. But then, after 3, the line starts to flatten out. That sharp bend right there at k equals 3, that's our elbow. The data itself is telling us that adding more clusters beyond 3 doesn't really help that much. So now we can put all the pieces together. We've gone all the way from a chaotic cloud of dots to a confident, evidence-based insight about the real hidden structure within our data. And here it is, our final result. But this time, it's not based on a lucky guess. We use the elbow method to prove that 3 is the right number of clusters for this data set. So this isn't just a pretty picture anymore. This is a real, meaningful insight that we pulled straight from the data. So, what are the big takeaways here? First, K-means is an amazing tool for finding hidden groups in your data. Second, it works using that simple, repeating process of assigning and updating. Third, and this is so important, choosing the right K is absolutely critical. And finally, the elbow method gives us a scientific way to find that perfect K. And you know, this whole process isn't just for random dots on a chart. It's used for everything from sorting customers into groups to analyzing medical images. So it really just leaves you with one final question. When you look at all the data in your world, what hidden patterns are just waiting out there to be discovered?